So we're relatively lucky on the Trinity River. This is the fall Chinook returns. This is pre-rod. This is before 2004, before the current flow regime on the river. This is after the implementation of those rod flows. And this is for fall Chinook. Is this good enough? Can you hear me good enough? Okay. Yeah. This is fall Chinook up here. You can see that we've done quite well relative to those other stocks. Pre-rod, post-rod, the population average has stayed steady. But you then ask the question, but the restoration program has spent many millions of dollars. Why do we only have a steady population? And there's some of those ocean conditions to explain that. There's also some of what I'm going to explain today to explain that. Down here are spring Chinook numbers. You can see we've been less lucky. The pre-rod numbers of spring Chinook salmon are about twice what they are post-rod. And so that's obviously not a desirable outcome of a restoration program. And I'm going to explain one potential reason in the river for why that might have occurred. So one aspect of the salmon's life cycle that the restoration program has direct influence on is the freshwater life cycle. And that primarily starts with the juvenile stage. So there's the egg stage, there's the eyed stage, there's the fry stage, and there's the smolt stage. That is all in the river, and that's what we have some control on benefiting through our actions. And you can see these are the population estimates for juvenile salmonids made at Willow Creek. They've been made since around 1989 until present. These are the data through 2018. You can see pre-rod, the number is down here. Post-rod, the number's up here. So with the rod flows, the fry production or smolt and fry production has increased by almost 3 times as a result of the restoration that's occurred. However, what we've also seen, and I'm going to go up here because this is a little hard to see, is that these are smolt sizes. So adult migrants are measured for their length, their fork length. That's from the fork in their tail to their eye. And the fork length for fish pre-rod are in these dark bars. And so from about March 15th through June 1st, the rod fish, the post-rod fish, are a little bit larger than the pre-rod fish. So we see before summer an increase in fish size as a result of restoration. However, in summer, we see the reverse. The restored flows in the river from the rod decision are producing smaller fish. So smaller fish is important to consider in the fact that larger juveniles have a better chance of surviving to adulthood. So why do we have larger fish going out during rod flows in the early spring, but we have smaller fish going out under rod flows in summer? That's part of what I'm going to explain. So look at this. This is the average daily flow for these different periods of record. The black line is pre-dam. So pre-dam, the fish had all these high flows. The fish are coming out of the stream bed around January, and they're hungry. They need to eat. They have these high flows, and you're like, oh, that can't be good for these little creatures, but it's super good for these little creatures because it gives them access to floodplains. Floodplains are the breadbasket for fish. So on floodplains, there's more bugs, there's more food overall for these creatures to feed on. So pre-dam, they had access to floodplains, and then when it came down to summer, oh no, the flows went down below 100 CFS typically. So you had a river that was twice the size as it is now with a quarter of the water that's in the river in summer now. That's the situation in comparison to rod flows, which are the red line. So what's happening with the red line is we have these grossly exaggerated summer flows in a channel that's half the size compared to pre-dam. I'll show you later what that effect that has on the fish, but now I'm going to explain this green line. This green line is post-dam but pre-rod. And so remember, the fish were somewhat larger before summer, pre-rod, under this green flow regime. And I think that's because not only did they have slightly more access to floodplains during this early rearing period, but they more so had lower flows that occur in summer under the rod flow regime. Lower flows in summer mean warmer temperatures. So these relationships between fish size, water flow, and river temperatures motivated funding from the TRRP for a river temperature study. And the question was, how can summer flows in the river be managed differently to improve adult habitat for fish and other species? That's the guiding question. But the hypothesis, the specific question we're asking, is that can flows that enable temperature stratification in pools, can they provide the thermal variability that juvenile salmon require to maximize their growth and provide habitat that adult spring Chinook salmon need in summer? So I'm going to back up a little bit. Why do juvenile fish need variable temperatures? So a juvenile fish needs variable temperatures because what they try to do is maximize growth as quickly as possible. They want to be as big as they can when they're entering the Pacific Ocean because they'll have a better chance of surviving if they're larger. So how they do that in the river is they'll feed to satiation, and that's typically in the early morning when temperatures are cold, and then they'll drop back from these riffle habitats where they tend to feed, or at the head of pools where the water's fast. They'll drop back into that cold, variable, sometimes warm, you'll see later, habitat in pools that has all these variable depths. And they can regulate their temperature by accessing different depths in pools that stratify. That's why temperature variability through stratification in pools is important to increasing adult salmon populations because it grows larger fish. Now, in terms of spring Chinook salmon, the adults, when they come back, what's been observed and published in the literature is that they will swim upstream in spring when flows are high, and they'll take advantage of thermal stratification by resting in pools during the day when there's that cold bottom water, and you'll see that here in a sec. And then when the pool stratification breaks down, they'll say, okay, it's time to move on. And they move up to the next couple pools. And that way they hop, skip their way upstream. That's why the springers need stratification for migration. They also need it for holding in summer. So when they get near their spawning grounds, they can sit in a pool, in the bottom of a pool, for months before they actually spawn. If they don't have slow, cold water and variable temperatures to regulate their metabolic processes, because they have eggs that they need to mature in their body. If they don't have that variability and that energy-saving slow water, they're going to run out of energy, potentially. They're going to have a hard time regulating the, development of their eggs. So that's the importance of stratification and the motivation for this study and the reason for it. So what then is stratification? It's a real simple concept. It's just the arrangement of water temperatures in a thermocline with warm water at the surface and cold water deep. And stratification is important is because, as I explained, it gives salmon and other species access to a wider range of temperatures than if the water is mixed, temperatures are uniform in the pool. So the importance of thermal stratification in Northern California, this is a natural phenomenon on undammed streams. So if you go to the Salmon River, you dive into a deep pool. If you dive from a high rock, you're going to feel the warm, and then as you go below about 2 meters, you're going to get real cold real fast. That is what provides adult spring Chinook the slow, cold water at the bottom of the pool. That's stratification. And they rest during the day during their upstream migration to spawning grounds at night. You see these fish, they're hanging out in some pretty slow water. That's not by accident. So once springers migrate to near their spawning riffle, they'll rest for months in the bottom of that pool. They need that slow water to preserve their energy so they can be more successful at spawning in fall. And then, as I explained, stratified pools provide juvenile salmon the variable temperatures they need to regulate their metabolism to maximize growth. So here's the study area. There's two pools. One is nicknamed PT pool. It's a pear tree pool. It's located at the downstream end of the restoration reach. And the other pool is located in the upper Trinity River. And so that's why it's called UT pool. And the UT pool receives unregulated flows. The PT pool receives rod flows that are fully regulated. So the setup for the environmental conditions for the study is that there are high cold summer flows released from Lewiston Dam, and those are intended to aid adult spring Chinook migration, but they may not provide suitable habitat for holding. We'll look into that in this talk. And then the juvenile salmon have increased in number post-rod, but fish are smaller. And the question is this due to cold, uniform temperatures, and that's in space, and I'll explain that in a second. In summer, that's our question. And then smaller juveniles, again, survive at lower rates to adult, and uniformly cold water may decrease future adult returns. So those rod flows, they're intended to benefit the salmon populations, may instead be detracting from them because it's lowering the juvenile survival to adulthood. We'll look into that. So here are the study pools. This is UT pool here, and this is PT pool. The pools were instrumented with pressure transducers at their inlets and outlets. Pressure transducers measure the weight of the water, and so you can know the height of the stream, and so also the discharge entering and leaving your system, your study system, which are the pools themselves. And then there are temperature stringers located in the deepest location of each pool. And those stringers are simply a weighted line with temperature monitors mounted on them with a float on the top. So you're basically measuring the vertical range of temperatures in the pool. This study occurred in year 2000, and here we show dots. Each one of those dots indicates a location where a temperature velocity profile was measured, and also our temperature and a velocity profile was measured, and also the flow depth. And that was done monthly over that summer. So just some details. The upper Trinity River pool, its summer base flow is about 0.5 cubic meter per second. So you're gonna have to do a little math. 35 cubic feet per second is 1 cubic meter per second. So the summer base flow at UT pool is about 17 CFS. The summer base flow at PT pool is about 480 CFS. So in terms of the max depth at that base flow, it's about 5 meters at UT pool and about 4.5 meters at PT pool. And then the PT pool is about twice as large as UT pool. So that's just context for these different study areas. So here's the results. This is UT pool. You can see these are the temperature stringer measurements, and you can see that the temperatures coming in and going out of the pool and existing in the pool plot as a single line at the beginning of summer. And that's because stratification doesn't exist. There's no temperature variability in space. There's temperature variability in time, but we'll see that in a second. You need, for stratification, temperature variability in space. And so here's when stratification first formed, which is June 28th. And stratification was formed and destroyed daily in this pool from June 28th until November 11th. And within that period, we can see that the temperature of stratification, which is this red line, which is the difference in temperature from the bottom to the top of the pool, was up to 8 degrees Celsius. And it varied depending on weather. So if it was a hot day and a cold night, you would have a higher degree of stratification. If it was a warm day and a warm night, you'd have a lower degree of stratification. And I'll explain why that works that way later. So the average period with stratification formed in UT pool was about 8 hours. The maximum period was 13 hours. And the timing of stratification forming and destroying has consequences, and I'll explain later. So here's the incipient stratification, or when stratification first formed. You can see those lines diverge from the line diverges from a single line into all these different temperatures at depth. The bottom temperature, or the coldest temperature in the pool, is the bottom line, and then the top temperatures are the temperatures that are measured in the top layers of the pool, also in the inlet of the pool. So the inlet temperature, so the water entering the pool, that's the inlet temperature, and then you see the temperatures going down with depth to the bottom of the pool, and that's what stratification formed. So stratification formed, like I said, on June 28th, right here. And it's hard to see. Oh, and by the way, stratification is defined as a vertical temperature difference of 1 degree Celsius, consistent with the literature. Stratification formed here, and you can see one of the important requirements of stratification is temperature variability in space or time. In this study system, the temperature variability was in time. And you can see the variability was higher previous to the stratification first forming. So if water density varies with water temperature, so warmer water is less dense and floats relative to colder water that's more dense and sinks, then why did it take until the temperature variability decreased for stratification to form? Anyone have a guess? It was the discharge. The discharge lowered below the critical value under these temperature conditions and the bathymetry of this particular pool to such a level that we had higher density differences in the flow previous to when stratification first formed, but it couldn't form because there was too much water entering the pool. Too much water entering the pool causes turbulence that mixes all those different layers, so the density differences cannot settle out into their different layerings. So the first lesson of our study was the number one requirement after temperature variability for stratification is a sufficiently low discharge for the stratification to be maintained. So once stratification first formed, like I said, it was reformed and destroyed on a daily basis. And you can see how uniform this variability in temperatures was. Stratification typically formed soon as the sun hit the surface of the pool, and it lasted until sunset. So let me walk you through this. This is fascinating. We're starting at midnight. This top little line, that I always have to look. That's the outlet water temperature. The pool is releasing in the middle of the night warmer water than it's taking in. This is the inlet water temperature. The inlet water temperature is colder than the outlet, so the pool is a thermal sink. It's releasing warm water downstream. The pool is also almost fully mixed. There's very little distance between these lines. These lines are the different depths of the pool, the temperature at different depths of the pool. That fully mixed state in the pool lasts until direct solar radiation hits the pool surface. As soon as that happens, we see divergence in temperatures, right? The stratification starts to form. This outlet water is now warmer than the inlet water. So the pool is starting to store heat. The pool is starting to heat up and store that heat that's being delivered to it from upstream. And that causes that cold bottom water pool to just stick in there. And all the water movement, all the flow through the pool moves to the upper surfaces of the pool surface. And so the only water moving through this pool predominantly is near the surface because that's where the top water entering the pool is being kept because it's so warm. It's buoyant. It sticks to the surface of the pool and moves downstream. But as time goes by, there's vertical diffusion that occurs in this pool and all pools that stratify. That vertical diffusion is that warm water mixing with the lower layers. And that displaces a portion of that cold water body that was formed overnight. That cold water then starts to take on heat, and there's this slow mixing period that occurs. That slow mixing period lasts until the shade at this particular location from trees and mountains starts to touch the pool surface. And at that point, we see the pool surface temperature decline below the outlet temperature. At this point, we're starting to see a fast mixing period. That fast mixing period causes a rapid collapse of the stratification. As you can see here, all these temperatures are rushing up. And so there is much less temperature variability because the stratification is being destroyed rapidly as the whole pool is recooling, moving into nighttime. So that's the cycle. After the sunset occurs, the pool returns to its fully mixed state that existed the previous night. And that is just repeated over and over and over. So what's the importance to fish here? Adult fish can go ahead and migrate at night when it's safe to do so because they're going over shallow waters. And let me say that I'm not speaking for all fish because there's variability in biologic populations. I'm sure fishermen in this room have noticed different things. This is what I've noticed. That the fish will tend to migrate at night. Sometimes if they're forced to, they'll migrate during the day. But here, during the day, they would be resting in this cold pool bottom. And then as soon as, or soon after, the stratification breaks down, there's no more cold water habitat for them to hide out in. And it's coming on darkness when they can migrate under relative safety. At the same time with stratification, look at the variability in temperatures that the juveniles have access to. There are a lot of juvenile fish that hang out in this pool, and just working on this pool for so long, you could see that they were accessing different levels in the pool at different times of day, and that's for temperature regulation. They do that as they need to, and it's possible because those variable temperatures are available to them.
But isn't this pool well above the dams?
Yep.
So you're not getting the flow of the Chinook or king salmon up there?
That's correct.
Okay.
Those are resident trout.
Okay, that's a whole different species.
I'm trying to visualize this pool. Is it as wide as the river is wide? Or are the fish have other choices other than the other pool? Or is it, you know what I mean?
Yeah, they do.
Visualize it.
Yeah, there's actually very few pools in the upper Trinity River. This is one of the deeper, larger ones. So yeah, they have access to other locations. I didn't survey other locations. I just stayed in this pool. So where else are the fish? I can't tell you because I didn't look. And these are, yes, not salmon that are accessing this pool. The idea here is not the specific case study, it's the concept of the process. The process that occurs here used to occur below the dams before the dams. And so what I'm trying to explain is the natural physical process that occurs above the dams is missing below the dams. And there's consequences to that.
Even in eddies?
Say again?
Even in eddies on either side of the pool, you have very little downstream flow. You have plenty of down.
So that is a good point. And yes, there is temperature variability on the pool, on the river edges. It's relatively low compared to pool stratification. It's quite a bit lower, like maybe in the range of a couple degrees versus up to 8 degrees at this location.
I noticed the pool's filling in with the gravel they're putting in the river. Some of our deep water pools where the fish cool and hide out during the day are getting shallower.
Yeah, that's a whole nother topic, and I can talk to you after this about that. Otherwise, yeah, because we could keep going on that alone for a while. So here are those velocity and temperature profiles I mentioned. This is for UT Pool. These are the flow velocities. You can see at a depth of about 2 meters, the flow speeds up, and that's at the depth of the thermocline. That's where you have this warm water. These are temperature profiles, and the temperature increases in this direction. So as you go upwards from the bed of the stream into towards the surface, you have uniform temperatures at depth, then it starts to warm up, and then right here it's near vertical. This is the thermocline. This is the top warm water that's flowing in this pool, as I described earlier. The bottom water is nearly still, as you can see these velocity profiles indicate. And so you're going to say, well, Buxton, that's not entirely correct, because look at the velocity profiles. They exhibit different temperatures themselves, and that's because they're measured at different times of the day. The river warms through the day. Each one of these lines is where one of these profiles was measured. So as you measure later in the day, the temperature profiles overall get warmer, and that's the reason for the shift in the profiles. So this is, I think, the coolest part of this pool, how the stratification period ended. And that was on November, I can't remember, but down here. And so if we zoom into here, we see that the end of the stratification period, or the last day that stratification occurred on a day that the air temperature got quite a bit below freezing. So you can stratify a pool with freezing air temperatures. Remember, all you need is a subcritical discharge and temperature variability. But at some point, no matter how low the discharge gets and how variable the temperature within the cold range of densities, you're not going to get stratification, because here is a water density versus temperature. You can see there's very little difference in density at these low temperatures. So you're going to have almost a still water to have stratification form under those conditions. And that's why, even though the discharge was about half at this period of the year than it was during summer when stratification was forming, it quit forming because the river temperature overall stayed too cold. So that's the end of the stratification period. So let's turn to Pear Tree Pool. It's a whole nother story. This is, again, at the lower end of the restoration reach, just upstream of the North Fork Trinity River. You can see the results of temperature measurements on the stringer. They plot as a single line, and that is because the pool is completely mixed. There's no stratification because there's too much turbulence by the high flow entering the pool and mixing the temperatures. The temperatures are just as variable here as at the other pool, but all those different temperatures are being completely mixed by the high flows. So there's no variability spatially in temperature for juveniles to access. There is suitable temperatures for springers to hold in. These are pretty much near ideal, maybe a little high, for springers to hold in. So we're providing the temperatures with our regulated flows for springers to hold in the restoration range. That is something to note. However, we're not providing the velocities they prefer to hold in the restoration range in summer. These are the vertical velocity profiles. At PT Pool, you can see that they range upwards of 1 meter per second. That's about 3 feet per second. That's fast water. And that's what these fish are being asked to hold in for months. It takes a lot of energy. You can imagine getting tired. I would bet the fish do too. They can find areas to hide. So this isn't like there's no habitat here. It's that it's not ideal habitat conditions for these fish. And then for the juveniles, here's the vertical temperature profiles. And they are vertical, aren't there? There's no temperature variability there. These were measured throughout the pool on each of these dates or months that the measurements were made. So you have no spatial variability in temperatures for the juveniles to access to maximize their growth. So what are you doing here? You're stressing the adults with high velocities with rod flows in this particular pool, and you're providing no temperature variability for the juveniles to rear in. That's not good for those adult salmon populations, especially the spring Chinook. So making the linkage to the difference between pre-rod and post-rod spring Chinook populations, we see the decrease, the decline. We also see an increase in summer flows in the Trinity River. I would bet those are not an accident. I think they're directly linked. However, that's just my thought. So from these two pools, we learned some things, and this is supported by the literature. The requirements for thermal stratification in river pools are a large pool volume, and that's to disperse the fluid momentum. And then you also need deep water, as I mentioned before, to attenuate that solar radiation. The water in the upper 2 meters of the pool will warm from the sunlight, so you need water deeper than that to get the cold water in the bottom of a pool. And then you need inlet temperatures that diverge in space or time. In our study, the inlet temperatures diverged in time. Examples of temperatures diverging in space is where there's a cold water seep or a hot spring pool nearby. And then mostly you need low discharge to prevent thermal mixing. The Trinity River below Lewiston Dam has all of these conditions except the low discharge in summer. Above the dams, it has all these conditions, and we see stratification forming. So this was an interesting result that I was very surprised by. So remember that we released 450 CFS throughout summer from Lewiston Dam, and by the time you get down to Pear Tree, because of tributaries and groundwater, you got around 480 CFS. And that's sent down the river, that 450 is sent down the river to aid in providing temperatures to these fish to hold throughout summer. The pool at the Upper Trinity, remember, has only, 15 CFS? So how many more times is that less than that higher discharge? So for 480 CFS versus 15 CFS, the daily average and vertically average temperature in these two locations were the same in the heat of summer. And so what we're doing is spending a whole lot of water to provide cold temperature when we could provide it for a fraction of the water cost if we lowered the discharge to promote thermal stratification in pools. Questions? Yes?
What are you saying when you say the Pear Tree pool? Just so you know, I've been on the Trinity probably 200 days over the last 16 years. I've probably been through there over 500 to 1,000 times. When you say pool, are you speaking of the pool that's up against the rock at the top, or the pool that's closer to the road, slightly downriver? Because I ask because 3 feet per second, no matter what flows you're talking about, I think that is, if you ask me as a person who's been there 500 to 1,000 times, I don't see where you're finding that unless it's incredibly high flows at the top of the top pool, or you're dipping your tools into a pool that's not really actually a pool. So what are you calling the actual pool to get this information?
So you know where the USGS gauge is, Trinity River above the Owl. So it's not that pool.
Right. It's
the next downstream pool. And let's go back to that since you have a question about it. This profile here was in a depth of just over 3 meters. And it measured up to about 3/4 of a meter per second. So these were all measured in the body of the pool, but not always in the full depths of the pool. We weren't interested in quantifying the speed of flow through only the deepest parts of the pool, because we want to know what the distribution of speed flows are throughout the pool, because we were also measuring the area of stratification at the same time, which is I didn't include in this talk, but that's the reason.
And your thought was that you think that a Chinook, a hatchery Chinook, would want to be hanging out at 3 feet per second?
No, I don't think they would. No, not according to the literature anyway. I know you can catch fish there all the time.
No, I'm not getting at that. I'm
Yeah.
just to put the fish to the science. I've never seen a fish hanging out perfect staging at anything that's 3 feet per second.
Yeah, that's kind of my point.
I'm sorry, I'm confused. That's why I'm asking.
Yeah, that's kind of the point, that these flows that we're releasing from the dam are generating such high velocities that it's intended to provide the habitat, but in many cases it's providing too high of velocities for these fish to come forward.
Oh, I see. So you're saying that the high flows potentially are pushing them, keeping them out of that pool, or either swimming up above them elsewhere?
That's the thought. Yeah. Thanks for your input. You've spent more days on the river than I have. So moving on, we learned what's required for stratification in this study so far, but we need a way to model stratification so that we can understand how changing flows to promote stratification actually works outside of our study pools. And so we worked with a scientist out of the Denver Technical Service Center in Denver, the Bureau of Reclamation. He is a genius and developed a 3D model that we tested in this study. And we tested them in both of these pools. This is what's called a computational mesh. And what it is, this is a bottom view of the upper Trinity pool. It's showing this part of the pool looking from the bottom. So we surveyed the pool. We know where the water surface is. We put those pieces of information in the model. It generates this mesh. It's a 3D mesh, so all three directions. And in the UT pool, there are 152,000 mesh cells that take up the area flow that we're modeling. And in each mesh cell, there are 6 nodes. And so that means there are 920,000 places where these calculations are made. And at the PT pool, it's even larger. And this is just to say that the computational requirements for this part of the study were huge. And so the question then is, how well did the model perform? And I didn't include that here. There are printouts of the paper we published on this research on the bar right there, and it explains all of that. The model did nearly a perfect job. So I'm going to show you some of the results from modeling that we've obtained so far, just to show you where we're headed. This is the restoration rates of the Trinity River. And each one of these numbers is the river mile of a pool location that we are modeling with that 3D model. So this is the 3D modeling part of the study. I'm going to focus in on Deadwood Pool. Here's Lewiston Dam. Here's Deadwood Creek flowing out. And here's Deadwood Pool. It's actually got 2 pools in it. This is a 2D rendition of the flow depth modeled for this location. The blue areas are where the 2-meter depth requirement for Chinook holding occurs in this pool at summer base flow. Okay, so then this dot right here is the deepest location in that pool, and I'm going to show you the 3D results for it. I'm going to show you the effect of the summer flows on holding habitat and temperatures in this pool. I lied a little bit. I couldn't fit the 450 CFS plot on here, so I put the 300. The 450 is even more dismal in terms of habitat. But here we see at 300 CFS, The plot's pretty cut off, but this is the typical summer range of temperatures at this location. It's a sinusoidal variability, and you can see that's the same as we observed at UT and PT pools. And then here's the flow velocities. I can't see because of this curtain, and neither can you because it's cut off, but they're above the range that springers hold according to the literature. Moving over, let's go ahead in the model. Let's drop the discharge down to 200 CFS. Let's keep the temperature the same. And we see the velocity decreases below the range that springers like to hold in. They like to hold in 0.15 to 0.4 cubic meter or meters per second. So that speed of flow is what, according to the literature, these fish like. This is too slow. 200 CFS is too slow. And we're not getting any temperature variability spatially at this location. So let's go ahead and just keep the temperature constant, lower it down to 100 CFS. Remember, this is a common pre-dam summer discharge on the Trinity River. And the river is about half the size now as it was before the dams because flood regulation has decreased the size of the channel. So we still have 100 CFS and a half the size channel. We're starting to see temperature variability. This line of temperatures is starting to widen. Slight differentiation in those temperatures is occurring, and you can see that affecting the velocity in this pool. Let's go ahead and zoom in on there. You can see this is the same plot, but with a smaller range in the y-axis, which is all whited out. But you can see there's more variability in temperature here, and that's, in water speeds here, and that's good, but it's not good enough. That amount of variability isn't really gonna get you much for fish. So remember that stratification depends on the range in water temperature and the discharge primarily. So let's pump the temperature in the model up to 10 to 25 degrees Celsius, keep the discharge at 100 CFS and see what the velocities do. We, at this point, start to see stratification form in this pool. As you can see, the temperature lines separate out. And coincident with these separations are these variations in flow. What we're providing now is nearly zero velocity at the pool bottom and providing temperatures in the pool top that are within the range that springers target for holding. And so earlier I said springers target those bottom depths of pools, not exclusively. We've all seen those cool pool pictures of pools that are deep in blue and the fish are on the surface swimming around. I don't know why, but they do use different depths in the pool. Maybe it's because of temperature, maybe it's because of other things. I don't know. Maybe in this case, those fish would use the upper surfaces of the pool. I don't know. But I do know there is no habitat for springers to hold in according to definitions in the literature until we get down to 100 CFS and we raise the temperature variability to 10 to 25 Celsius. So where are you going to get the temperature variabilities? You're near the dam. So as part of this Trinity River temperature study, we are monitoring temperatures in Lewiston Reservoir. This is the second year of that monitoring that's occurring. I'm only showing you the vertical temperature profiles that are nearest the dam. They extend up to the power plant at Trinity Dam. But right here, vertical 11, that is at the radial arm gates that release top surface water to the river. Vertical 12 is the power and intake for water, and also the bypass valve. So we can use this for drawing from the bottom of the reservoir where temperatures are coldest. And then here's the car diversion. We can kind of ignore that, but it just shows here that the temperatures measured in this profile to car diversion are a little bit lower, but not a whole lot than at this vertical 12 inlet, which is for the hatchery and the bypass, and then the radial arm gates at vertical 11, which is where the temperature variability is the greatest. So the study is trying to figure out how we can draw from these different outlets to provide the temperature range that is needed to meet the habitat requirements in the river, given the findings that we have from the stratification study. That is the reason for this reservoir study, is we want to be able to provide fish in the habitat in the upper Trinity River, where their spawning density is the highest in the entire Trinity River. So it makes sense to study the reservoir, which is providing you the flows and temperatures that you need to provide those habitat requirements. And so, Buxton, what happens if you drop the river down 100 CFS? What do you think that's going to do to the rest of the river? That's fine and dandy up by Deadwood Creek, but it's maybe not fine and dandy elsewhere, and you're exactly right. So we're also modeling the temperatures in the entire river from Lewiston Dam down to the North Fork Trinity River. We're doing this with a model the U.S. Army Corps of Engineers developed. It's a 1D model. It's a flow and temperature model. And basically, you can change the discharge and the temperature at your upstream end. It accounts for tributary inputs of flow and temperature. And then you can track the temperature changes through each one of these cross sections all the way down to the North Fork. There's over 1,000 of them. And so what we can do with this model that has been calibrated in the upper river, this is the results of the calibration. The line here, the light line is the observed, the dotted line is the modeled. The model's perfect so far, but then as you move downstream, it starts to diverge from the observed temperatures, so there is more work to be done on this. It should be complete by mid-November, then we'll be off and running. And so we can then ask the question, okay, what happens if you release that 10 to 25 degrees Celsius water out of the dam at 100 CFS? Where does it become deleterious to people and creatures downstream? And it's going to be a dynamic balance between all these considerations that we've discussed here today on what a summer flow regime that's healthy for the Trinity River, recreation on the Trinity River, and power generation from the dam. That's the goal here, is to know that answer. It's going to be a seasonally variable answer, but that is the goal of all this research. So here's the summary slide. Naturally low summer flows in the river above the reservoirs enable temperature stratification in pools, but below the dams, the unnaturally elevated releases prevent stratification and generates spatially uniform temperatures and high velocities in pools. These conditions prevent juvenile salmonids from accessing warmer and variable temperatures to maximize growth, and they also prevent adult salmon from holding in cool, deep, slow water in the regulated portion of the river. This is from the literature pre-dam on the river. Spring Chinook salmon held in those stratified pool bottoms in daytime until the river cooled for migration to resume at night. But currently, the high flows that prevent stratification are actually forming thermal barriers down in Hoopa. And so we have to sometimes release higher summer flows to get those fish to be able to migrate up because of that effect. So this can prevent those fish from making their way upstream towards the dam. And this could be mitigated by temperature regulation that's provided for by pool stratification, as I explained. This is that interesting result that daily vertically average temperatures with stratification were close to the same as the pool without stratification, despite discharge being so much less. So lowering dam releases to stratify pools can provide warm and cold water habitat with much less water than is currently released in summer. And then the water savings can be used for environmental benefits at other times of year. And just to recap, that TRP is investigating how river flows and Lewiston temperatures can be better managed to provide summer river temperatures that increase salmon populations in balance with power generation and recreational demands on flow. As I mentioned, this work has been published. The top publication is printed right out there on the bar if you want to grab one. And then the 3D model that I mentioned has also been published And you can probably access that online. It might be on the TRP data portal as well. But that's all I have.